Chapter 1 for Griffiths' Introduction to Quantum Mechanics. And that's problem 1.14. This is not a hard problem. It's a little lengthy, but it's not bad. It just pretty much encompasses all the stuff that we've done thus far. Normalizing, finding the potential energy to satisfy the Schrodinger equation, and getting these expectation values so we can actually compute out the uncertainty. The first part's pretty simple. We're just going to normalize it. Now our wave function, capital Psi, has this normalization factor A, and it's an exponential, some constant, I'm assuming a constant A, mass M, and it's a Gaussian, and then plus IT. So I did read a bit ahead, and I realized one of the reasons I thought problem 1.13 was a little trivial is because I didn't realize that he hadn't gone over separation of variables yet. I guess I kind of assumed a bit too much. So that being said, the next video on chapter 2 will be about separation of variables. So for now, we're just going to stick with our earlier proof that we can normalize at t equals 0. Meaning that my psi is a function at t equals 0, and we just get a straight up Gaussian. Now, to normalize it, we must be able to find it over all space. So we are just going to integrate the wave function squared. That's this guy, minus 2am over h bar x squared. I'm going to go ahead and just do simple u substitution for this. Although in all honesty, I do usually use integral tables instead of doing these all by hand, generally. Okay, so my u is just going to be the square root of all those constants times x, meaning du dx is just this. It's a good habit to get into, to, you know, keep up doing all of these by hand, which I really haven't kept up with as well as I think I should. I think it helps with other problems later on to have the basics down better. That being said, when I do the expectation values, I am just getting those out of a table. Okay, so now we're replacing du with dx. So, oh, whoops. Anywhere that I had a dx, I am now replacing it with this term. My limits, if I plug in positive infinity and negative infinity, they don't change. Okay. And then we just have e to the u squared, meaning this guy comes out in front here, and that integral of our Gaussian at that point, so over all space, Gaussian is just going to be square root of pi. So then we get square root of pi. Oh, and I had my a squared. That's the whole thing I'm solving for. There we go. So what I get is 1 equals square root of h bar pi over 2am capital A squared. So my a is going to be 2 times a times mass over h bar times pi, all to the 1/4 power. Pretty straightforward normalization there. Now it wants to know for what potential energy function V does psi satisfy the Schrödinger equation. This does kind of get back a little bit to that separation of variables deal. So I have my Schrödinger equation, I h bar over 2m del psi del x squared minus h bar over I v psi. And it wants to know for what value of that potential energy function do you have a solution such that psi equals, now we know A, and then we get, it's the 1/4, that was negative a mx squared over h bar plus it. And what we've seen in our earlier problems, and what we'll also see from our separation of variables, is that our potential energy is going to be directly related to, I forgot the A there, to that time dependent term. So I can go ahead and split this up, just parsing out that exponential, and what I get is e to the I a t. And I can approach this just by looking at units here, but we have seen it in earlier problems as well. The units inside an exponential have to cancel out. So if my time has units of seconds, then that means my A must have units of hertz, or inverse seconds. So that means that my A is corresponding to my frequency, and my potential energy is my frequency times h bar. That's just purely from units there. I have this h bar, negative h bar I, out there for a reason. We will see explicitly with the math when we do separation of variables. But what I have is that my exponential to the negative h bar over I v t. So basically my A is corresponding to that frequency, meaning that my potential energy must equal this frequency that I have in here, this A, constant A, times h bar. And that's the potential energy that satisfies the Schrodinger equation. And we can make the argument based purely on units. We could also do it probably more effectively doing a separation of variables, but I'm going to go ahead and save that for when we start chapter 2, because given the fact that he was not expecting you to maybe apply separation of variables to the Schrodinger equation, he starts chapter 2 by explaining why you can do it to the Schrodinger equation. So I think he was looking for a more qualitative argument here. I could be wrong about that, but it seems like that's all that was being asked for. Okay, next we're going to calculate, getting towards the end of the page, so I'm just going to go ahead and grab a new page. Going to start calculating these expectation values. And yeah, I will be using certainly more integral tables. Well, at least one more. Okay. So for C, let's start with calculating X. This one is fairly trivial. Our expectation value is going to be over all space dx psi complex conjugate x psi. In our case, we're going to get that A factor out in front. I already forgot what it was. 2am over h bar pi. am over h bar pi. This is going to be a squared, so that's only going to be the 1/2 power. Then I have my integral over all space over x. I'm still going to be doing this for t equals 0. We could just have that time factor come out of the integral, but it makes more sense to just do it for time equals 0, like a stationary state, and then add it back in if we want to talk about a dynamic state. Oh, and then we have 2 of those over h bar. So this integral equals 0 because it's odd. Because we will get a specific constant value that I can get from an integral table if I do from 0 to infinity, but then I have to do the same thing again from negative infinity to 0. So we get this guy here. So from 0 to infinity, we are going to get a constant value. It's going to depend on that factor there. So in our case, we would have n equal to 1, and we get 1 minus 1, and it all goes away. We'd also have to do the same thing for negative infinity to 0. So yeah, it ends up not being that important to us. And our expectation value is 0. When I first did this, I did actually work it out by doing a integration by parts, which is certainly possible. So you can, and it's probably a good exercise. I just personally kept messing it up and kept relying on the fact that I know that it's 0. So duv So you can use x as u. So du is just 1. And then you have the integral of that guy. And then you have uv. But you'll see quickly that that does not converge. So there's also another trick you can do. So you can do that, although it gets annoying pretty fast. The other thing that you can do is you can first do a u substitution and then do integration by parts, and that's a little bit more successful. So if you do this whole thing is u, then my du dx comes out to 4 over am over h bar x, but then when I solve that for dx, I get h bar over 4 am over x, and that cancels out my x. So now my integral is just going to be dependent on x. But here's where we get into a little bit of a thing. First, before I do that u substitution, well, actually we'll just throw it in there so you can see what the issue is. So I'm integrating from negative infinity to infinity, and now I am, whoops, there's my du. So now I have du h bar over 4 am x times x e to the negative u. That cancels out. Now I'm just integrating e to the negative u. As I'm sure you can see right now, the issue that I'm getting is that this integral doesn't converge. If I go ahead and take the other, integrate them separately from 0 to infinity, take out this guy. Now I'm just integrating from 0 to infinity. I think I'm safe in just putting in the result here, because that's just going to be a negative, that whole stuff. And then we just get like a constant out there. So I get e to the negative 0 is just 1. So I just get that guy minus 0. Then we have to add, oops, I don't know why I put a 2 there. Then we have to do our integral from negative infinity to 0, and we get another constant out there. We end up getting this guy again, because then we flipped our signs. Minus, minus. Or you can just plug it into Wolfram Alpha and it will tell you it's 0. So we just get nothing there. So our expectation there is 0. Then, and I have all of this other junk out here too. I went through it from several different ways before, just trying to find something that would, every way I looked at it was like, oh yeah, it's just 0. And then I finally just gave up and it's like, yeah, it's just, let's just use the integral table. Let's not make this too hard on myself. That is what they're there for. Okay. So expectation value of x is 0. We expected that because it's odd. Now let's do expectation value of x squared. This is not odd and it is not going to be 0. So we are now going to have, actually I will just keep this up. We're going to have this form, complex conjugate, so x squared psi alright, this guy is going to equal, and I'm apparently going to put my constants inside there. So I have my a, which is this guy here, and I have my h bar pi to the 1/2, and then we have e. Again, we are doing this for time t equals 0, so we are, since we normalized in a stationary state, we are